So exam 2 covers chapters 5 through 8. So if we start off way back at the very beginning of chapter 5, it was asking you whether data was discrete or continuous. So if we have these different pieces of data here, number of customers at a restaurant, miles driven, some of it's going to be discrete, some of it's going to be continuous. So if we want to figure out the difference between those, discrete is going to be like definite numbers, right? Continuous can be any number under the sun. So the number of customers at a restaurant. Well, you can't have a quarter of a customer, right? You can't have 2.25 customers at a restaurant. So the number of customers at a restaurant will be discrete. It has to be 1, 2, 3, 4. It can't be decimals. It can't be fractions. So that's what makes that discrete. Then, miles driven on your daily commute. Well, do you have to drive 1 mile, 2 miles, or 3 miles? Or can you drive anywhere in between? Well, we can drive a quarter of a mile. We can drive a tenth of a mile if we want. So your miles driven on your daily commute will be continuous. Now, time spent waiting in line. Well, let's work it through again, thinking like minutes. Do you have to spend 1 minute or 2 minutes or 3 minutes in line? No, you can spend any amount of time in line, so that data is continuous. And then phone calls made by customer service representatives last month. Well, can someone make half of a phone call? No. So the number of phone calls is discrete, just like the number of customers, right? So if something is a definite number, it's discrete. If it can be any possible number, then it's going to be continuous. So now we move on to figuring out whether something is a binomial or a Poisson problem. So this first question here says, what's the probability that at least 5 of the 12 flights today arrive on time? Past data shows that flights arrive on time 60% of the time. So we need to figure out if this is binomial or Poisson, and then we need to find the probability. So we first look at the information that we're given. We were given an n of 12, right? N is your sample size. That's the number of flights. So there were 12 flights, so 12 is our n. P was 0.6 because we were told that flights arrive on time 60% of the time. So we have an n and we have a p. So there's a few different ways that we could go about this problem to figure out if it was Poisson or binomial. One of the ways is if you have your formula sheet in front of you, you take a look at the formulas for binomial versus Poisson. Well, for Poisson, you don't need an n or a p. So that sort of crosses out Poisson. Then from another perspective, we can tell that it's binomial because binomial means yes, no, right? There's either a success or not success. So these flights either arrive on time or they don't arrive on time. So that's what tells us that this question is a binomial problem. So that's really the first hurdle when solving a problem like this, is figuring out, okay, what am I supposed to do? What formulas am I even supposed to look at on my formula sheet? Then once you do that, then you can start filling in the information that we know. So now we can talk about finding this probability. So what's the probability that at least 5 of the flights today will arrive on time? So we are going to want to take a look at our cumulative binomial table. So you guys have that booklet that Sam Bloom gave you with your binomial tables, your Poisson tables, your z-scores. So we're going to want to find the cumulative binomial table in that set. And we want at least 5 here. So in that table you have your p's, your n's, your x, and we know our n and our p already. That's the 12 and the 0.6. The x is where things get a little tricky. So at least 5. So if we draw a number line here from 0, which would go all the way up to 12, at least 5 means that group, that 5 or more. So we want to know the probability that all of those end up arriving on time. But it's going to take a while to add up all of those individual probabilities. So by using our cumulative binomial table, what we can do is we can take a look at the x equals 4 of that table. Because if we do that, that's going to give us the probability of 0 through 4. So if we have the probability of 0 flights through 4 flights arriving on time, we can then take that probability and subtract it from 1 to find the probability of at least 5. So when you look in your table, you'll see that the cumulative binomial probability for x equals 4 under p of 0.6 and n of 12 comes out as 0.0573. Then, at least 5, we subtract that from 1. So the probability that at least 5 flights arrive on time today is 0.9427. So, when you are working on a problem like this, make sure you read closely to find out what it's asking for. If it's asking for a probability, we know that probabilities have to be between 0 and 1. So the probability is 0.9427. If they were asking for what percent chance is there, then we need to take the 0.94 and turn it into a percentage. So if they were asking for what's the percent chance that at least 5 flights arrive on time, our answer would then become 94.27%. So make sure you don't lose points when it comes down to just how they want the answer given. Right? So probabilities have to be between 0 and 1. Percentages, that's when we multiply it by 100 and put that percent sign on there. So now this next part. If the average number of customers to come into the store in an hour is 20, what is the probability of exactly 6 customers arriving in 30 minutes? So we need to figure out, is this a binomial or a Poisson problem? Well, we have the information over on the left. We have our mu, which is 20 per hour, and we have our x, which is 6. Again, we could look at our formula sheet and see that the formula for Poisson distribution needs mu, x, and then e. So we have mu and we have x. So that's one way for us to know that we might be going down the Poisson route. Another way that we know is that our mean is given in terms of time. It's that per hour in our mean. So whenever you have a per hour, per day, per year, that tells us we are dealing with Poisson. So it is a Poisson problem. Now, what is the probability of exactly 6 customers arriving in 30 minutes? Well, there's one step that we need to do before we can even work on this problem to figure out this probability. We need to change our mean to match what the problem is asking. Right now, our mean shows 20 per hour. But they want to know the probability about customers arriving in 30 minutes. So we need to turn our mean into per 30 minutes. So if we had 20 customers in an hour, we can assume that we're going to have 10 for every half hour. So we now have our new mean that we're going to be using in this problem. Our x is still that 6, right? The probability of exactly 6 customers. So then what can we do? Well, we can look up in the individual Poisson table, right? So that's going to be after your cumulative binomial tables in that packet that you have. And the information that we have here is our mu and our x. So we find our mu of 10, we find our x of 6, and then you will find your probability to be 0.0631. Now, you might be given some sort of situation where your mean doesn't show up in those tables. I think those tables show like 10.5 and 11. But what if your mean was 10.6, right? If that's the case, then we have to go with the formula. So let's work through the formula here for Poisson. So our formula on our formula sheet is mu to the x power times e to the negative mu, all divided by x factorial. So our mu, that's our 10, right? We want to use 10 here and not 20 because we want our mu to be in terms of 30 minutes. So our mu is 10, our x is 6, and e is just that constant on your calculator, right? So when we plug in the numbers here, we have 10 to the 6th power times e to the negative 10 all over 6 factorial. And when you simplify that down, you end up with the same answer, 0.0631. So there's a few different ways that you can solve these problems. You can use the tables, you can use the formulas. Either way, you'll come out with the same answer. So now question number 3. It says the average sales for your company is $300,000 with a standard deviation of 25,000. What do your sales need to be in order to be in the top 9%? So let's talk about what we have here. Our mean is 300,000, and we want to know what do our sales need to be in order to be in the top 9%. So that means that the area to the right in that tail has to be 0.09. Well, how are we going to figure that out? Well, we have a mu of 300,000. We have a sigma of 25,000. And we have that 0.09 area. We can use a z-score formula to our advantage here.
Wait, real quick, can I ask
Yeah.
a question?
Yeah, definitely.
Just to double check, mu and sigma are population mean and population standard deviation?
Correct.
Okay.
Correct.
All right,
Yep. So we have our z-score formula here. Right? We have our mu, we have our sigma. Those were given to us. Then we have z and we have x. Well, what we'll be solving for here is our x. We want to know what our sales need to be. So that's our x value. There's a way that we can find our z-score though. So when we plug in everything that we know, we end up with z equals x minus 300,000 all over 25,000. Now, if we take a look at our z-score table, and we want to know what z-score has an area to the right of 0.09. Well, if it has an area to the right of 0.09, that means it has an area to the left of 0.91, right? Because the area underneath the bell curve is 100% or 1. So if we look up in our z-score table, and we're looking up in the middle portion where all of the areas and probabilities are, and we're looking in there for 0.91, you'll find a z-score of 1.34. So now we just need to solve for x. So we multiply each side by 25,000, right? And what you're doing there is you are multiplying 1.34 times 25,000. 1.34 is your z-score. All a z-score is how many standard deviations away from the mean you are. So we're 1.34 standard deviations away, which would be the same thing as saying we're $33,500 away from the mean. Now, we just solve for x, and we find our x equals $333,500. Meaning, we need to sell $333,500 in order to be in the top 9% of our sales. So question number 4. The average price of a new car is $33,000, and the population standard deviation is $3,500. 500 people bought new cars in Phoenix last month. What is the probability that a random sample of 45 car buyers in Phoenix last month spent within $1,000 of the average price? So we are now getting into sampling distributions. Right? We want to know, based off of this sample that we have, the probability that this random sample spent within 1,000 of the average price. So we need to prove that our data here is normally distributed. So we have those 3 proofs for when we have a mean? Well, the one that we're going to use here is that our n, our sample size, is greater than or equal to 30, and sigma, our population standard deviation, is given. So that's our proof. Our next step is we need to now draw the bell curve. So we draw the bell curve and we put our mean on the bell curve. So when we're working through sampling distribution problems, we first prove it's normally distributed. We draw the bell curve with the mean in the middle. And then we need to solve for our standard error. So our standard error of the mean will be sigma over the square root of little n times our finite correction factor. Right? That square root of big N minus little n, that's our finite correction factor. And there's a certain time and place that we can use that. So if your sample is greater than 5% of your population, then you can use that finite correction factor. You can think of it as a type of reward for having a large enough sample size to represent your population, right? So we said that our little n, that's our 45. That's our random sample of 45 car buyers. Our big N, our population size, that's how many people bought new cars in Phoenix last month. So that was 500. So if we do 45 divided by 500, we get 0.09. So
can I ask you a question?
Yeah.
Sorry. So if n needs to be greater than or equal to 30, why does that not have anything to do with the population size? Why is 30 enough? What if the population was like a billion people?
Well, so n has to be at least 30 if we have sigma, right? So if we have the population standard deviation, then we only need a sample of 30. When you're working with like actual statistics out in the real world, it's very difficult to have sigma.
Okay.
And so that's when it's more likely that you need at least a sample of 100, right? The other proof is n is greater than 100. So that's probably going to be more likely when you are out in like the real world.
Okay. All right. Thank you.
All right. All right, so back to our finite correction factor here. So our sample is 9% of our population. So we did a pretty good job getting a large enough sample, which means we are allowed to use the finite correction factor. So we're allowed to plug in our numbers into the square root of big N minus little n over big N minus 1. If it was not greater than 5%, we would just totally forget that the finite correction factor even exists. Our standard error then would just be sigma over the square root of little n. But we can plug in the numbers that we have. So sigma was 3,500 divided by square root of 45 times the square root of 500 minus 45 all over 500 minus 1. So that's going to give you a standard error of roughly 498.
How do you know, like, which end, like, how do you know the little n is 45 and the big N is 500?
Well, so we know that little n is 45 because it tells us that a random sample of 45 car buyers, right? And little n will be the sample size.
Okay.
And then we just look to find if we were even told how many total car buyers there were. Sometimes you won't have that information, right? Sometimes they will only give you a little n, and they won't give you the full population size. And in that case, we can't say if our sample is greater than 5% of our population if we don't even have our population data. So we now have our proof, our bell curve, and our standard error. Now we can take all of that to now help us figure out what they're asking in this question. They want to know the probability that a random sample of 45 car buyers spent within $1,000 of the average price. So we draw our bell curve, right? And we have 33,000 in the middle. That's our average price. Well, they want to know if our sample spent within $1,000 of that. So we add and subtract $1,000 to our 33, and that's how we get that 32,000, and we get that 34,000. Now, when we have a bell curve and they want to know the probability of something, we should immediately be thinking z-score. Now, I don't think you have this formula on your formula sheet, but when you are dealing with sampling distributions, our z-score formula will be x minus x bar over our standard error. So, our x, that's going to be our 34,000 and our 32,000, right? Because we're going to need two separate z-scores here. Our x bar, that's our 33,000, like we have over on the left side of the screen right now. And our standard error, that's what we just found in the last part of the problem. So we can plug in our numbers here. We need to find the z-score for 32,000. So we do 32,000 minus 33,000 over our standard error that we found. And then we also need to find the z-score for 34,000. So we do 34,000 minus 33,000 over our standard error. And when you work through that, you will find that your z-scores are negative 2.01 and positive 2.01. So before we work through and figure out the probabilities, if you see a problem like this, where you need to find the probability that they spent within $1,000, well, you'll notice that the numerator for the formula on the left is negative 1,000, and the numerator for the formula over on the right is positive 1,000. Since you are equal distances away from the mean, our z-scores are just going to be plus and minus 2.01 in this case, right? They're the same number, just one is positive, one is negative. So you can maybe save yourself some time there when calculating a z-score. So now we take a look in our z-score table, right? And we can take a look at negative 2.01 first. And so we need to figure out the area to the left of that. So the area to the left of the z-score of negative 2.01, you'll find that to be 0.0222. So that's the area over in that left tail right now. But we want to know the area between 32 and 34. So in order to be able to calculate that, we also need the area from 34,000 all the way to the left. So when we look up positive 2.01 as a z-score, we get an area to the left of 0.9778. So now to be able to find the area between those two z-scores, right, between 32,000 and 34,000, to find that area, we subtract the two that we found. We take 0.9778 and we subtract 0.0222, and we end up with 0.9556. So that 0.9556 is the area between 32,000 and 34,000, which means that it's also the probability that this random sample of car buyers spent within $1,000 of the average price. So the probability is 0.9556. We could also rephrase that. If they were looking for the percent chance, that's 95.56%. So you can use these z-score formulas in multiple ways, right? We found z-scores in a normal way in this problem. In the last problem, we manipulated that z-score formula to find our x, right? So you just find what you need for each problem based off of the formulas that you are given. Now let's work on some Chapter 8 examples here. So in Chapter 8, confidence intervals came into play. So this problem that we're given says a sample of 55 days showed the average temperature to be 85 degrees. The population standard deviation is 4 degrees. We need to provide a 95% confidence interval for the population mean temperature. So we know that our n is 55, right? N is our sample size. They tell us a sample of 55 days. So we can write down n is 55. We also know that our x bar is 85. X bar is your sample mean. And our sample showed an average of 85 degrees. So our x bar is 85. We know that our sigma is 4. So it tells us the population standard deviation is 4 degrees. So we can work on a proof here to show that it's normally distributed. So our proof is that n is greater than or equal to 30 and sigma is given. So if you look on your formula sheet, you'll see a couple different confidence intervals for a mean. We have the one that mentions a z-score and sigma, but then we also have one that's a t-score and s. So if we're able to prove that it's normally distributed, that means that we are going to be using the formula with the z-score. So we can write out that formula now. So we have our x bar, we have our sigma, we have our little n, right? There's a few pieces in there that we don't have quite yet. There's that alpha. So over on the left, we have now that alpha equals 0.05. Well, how did we find that? Well, your alpha is going to be 1 minus your confidence level, right? So you are 95% confident in this problem. So 1 minus 0.95 gets you 0.05. But you can notice that we need the z-score for alpha divided by 2. So alpha divided by 2 is 0.025. So now we can plug in the information that we have here. Right? Our x bar is 85, plus and minus this z-score of 0.025, which we're going to have to figure that out in a bit, times 4 divided by the square root of 55. You'll notice we're not using the finite correction factor here, because our finite correction factor requires us to know the population size. But the problem never told us a population size. So we don't even use that finite correction factor because we don't have big N, so we can't just make up a number to plug in there. But now to figure out this z-score that we need the z-score for 0.025. So you're going to be looking in your z-score table again, and you want to take a look in the area portion, right, in the middle part of our z-score table. And we're looking for 0.025. And you'll notice that the corresponding z-score will be 1.96. Right? You could see it as negative 1.96, right? Because that's the z-score that has that area to the left. But since we have a plus or minus right in front of that z-score, we can just drop that negative when we plug it into our confidence interval formula. So now, our confidence interval shows 85, which is our x bar, our sample mean, plus and minus our z-score for 0.025, which is at 1.96, times our standard error of 4 divided by the square root of 55.
Wait, how did you get 1.96?
So if you take a look in your z-score table, and in your z-score table you'll have all those areas in the middle portion of that table. And so we want to find, in those areas, we want to find 0.025, which is our alpha divided by 2. And once we find that, then we see, okay, what's the z-score that has that area? And that z-score will be 1.96.
So do you not add like the negative?
So we don't need to have the negative here because we have the plus and minus in front of it. So we would be adding and subtracting a negative z-score. So we can just kind of drop that negative when we plug it into this formula.
Okay, thank you.
So before we work on the rest of the math in this formula, let's break down what each of these pieces are. Right? So everything after the plus and minus, that's called your margin of error. Right? The z-score and your standard error together is your margin of error. Then that 4 divided by the square root of 55, that's your standard error. So your standard error and your z-score together make up your margin of error. So if we multiply that z-score times our standard error, we get 1.0571. And that's going to be your margin of error. So now, if we take our 85, which is our sample mean, and we add and subtract our margin of error, we get a confidence interval of 83.94, less than or equal to our mean, which is less than or equal to 86.0571. So we can say that we're 95% confident that the population mean temperature is between 83.9 and 86.05 degrees. So, as you end up becoming more and more confident while making confidence intervals, the higher confidence level is going to make you have a larger margin of error, which gives you a wider interval. Right? So if we keep this temperature thing going on, right? I'm looking out the window right now. I can say that I'm 100% confident that it's somewhere between 20 degrees and 150 degrees outside. Right? So with a lot of confidence, my margin of error is going to be a lot bigger, which gives me a wider interval. But I'm only 10% confident that it's between 75 and 76 degrees outside. Right? So as I became less confident, my interval got narrower. So higher confidence ends up giving you a wider interval, and lower confidence ends up giving you a narrower interval. Now, the larger a sample is, will also have an effect here, right? So a larger sample is going to give you a smaller standard error. And if our standard error is smaller, then our margin of error will be smaller, which will give me a narrower interval. Right? So if I take a larger sample, that means that I have more data on all of the population. So the larger the sample that I have, the more exact I can be. So the larger the sample, the narrower the interval. And we can flip that around and say the smaller sample that we have, if we have a smaller sample, our interval will be wider. A few other things that could pop up on an exam. Your interval, right? That answer that we have down in the lower right now, that's our confidence interval. That's always going to be 2 margin of errors wide, right? Because we added and we subtracted our margin of error from our mean. So our interval ends up as 2 margin of errors wide. All right, so you're also able to use or make a confidence interval for a mean using a t-score, and we'll touch on t-scores a bit later on in the review. You can also make a confidence interval for a proportion. The process is all pretty much the same, right? I cannot stress enough how important it is to write down all of the information that you're given when looking at a problem like this, right? Figuring out, okay, your n is 55, your x bar is 85. All of that is going to be so important while solving problems, right? Because then you can just start plugging in numbers into formulas, right? Rather than having to go back and reread a problem and figure out what each piece is every time. So that's going to be your confidence interval. Let's work on finding z-scores again, right? So sort of like how we had to find that 1.96. You've probably in lectures or in your homework dealt with 1.96 and maybe a few other common ones. But if we have some more uncommon confidence levels, things could get a little bit tricky, right? So let's first find the z-score for a 90% confidence interval. So remember, the first step is to find our alpha. So we find our alpha by taking 1 minus our confidence level. So 1 minus 0.90 gives you that 0.10, the 0.10, right? But the z-score that we're going to need is the z-score for alpha divided by 2. So we divide our alpha in half, and we get an alpha divided by 2 of 0.05. So what is the z-score for 0.05? Now this one's a little tricky. So we take a look in our z-score table again, and we are looking for 0.05 as our area. So we're looking in the middle of our z-score table for 0.05. And you won't find it. What you'll find is that it's exactly between two different z-scores. It's exactly between 1.6 or 1.64 and 1.65. So, since it's exactly between those, what we're going to need to do is take the average of those two z-scores. So if we do 1.64 plus 1.65 and divide by 2, your z-score will end up as 1.645. Now, if one of those areas was closer to 0.05 than the other one, we would end up just taking whichever z-score is closer. But since this one was exactly between two z-scores, we end up averaging those two z-scores. So, if you ever run into a problem where you're dealing with a 90% confidence interval or your alpha is 0.10, remember that your z-score for 0.05 is going to be a little bit different than all of the other z-scores that you've seen. Right? We now have 3 decimal places. We have to average out a couple z-scores to find that one. So, let's work on this one. Your confidence level is 82%. So if we first need to find our alpha is 0.18. Right? If we do 1 minus 0.82, we end up at 0.18. So we need to take alpha divided by 2, and we get 0.09. Now, we need to find the z-score for 0.09. Well, if you recall, all the way back when we were trying to figure out what our sales would have to be in the top 9%, we've already found this z-score. So if you look in your z-score table for 0.09 as an area, the z-score that it gives you is 1.34, right? Or negative 1.34. So at an 82% confidence level, the z-score that you would use in a confidence interval is 1.34. Now this last one here, a 77% confidence interval. Well, so your confidence level is 77%. If we do 1 minus 0.77 you end up with an alpha of 0.23. 1 minus 0.77 equals 0.23. And we need an alpha divided by 2. So if we do 0.23 divided by 2, we'll end up at 0.115. So just like we've done in parts A and B, we need to find the z-score now that corresponds with the area of 0.115. So we're looking for 0.1150 in our z-score table, right? In the area portion of our z-score table. And the z-score that we find that matches up with 0.115 is going to be 1.20. So you can practice like this before your exam, right? Give yourself just random confidence levels. 61% confident, 93% confident, right? And just give yourself random numbers, find your alpha divided by 2, and then find that z-score that would match up with that, right? The more comfortable that you are using that z-score table, the better you will do on your exam. So, we have one more question here. We now need to find all of our t-scores. So, when you're working in confidence intervals, if you aren't able to prove that it's normally distributed, then you're going to need to use a t-score. It's slightly different than a z-score. So you'll notice that I not only gave you how confident you are, but you also need to know the sample size in order to find a t-score. So after your z-score tables in that packet that Sam Blum gave you, you'll have a t-score table, right? So we'll want to take a look at that here for this problem. So this first one, 98% confident and a sample size of 45. Well, when we're trying to figure out t-scores, we need to know something called degrees of freedom, right? So if you're taking a look at your formula sheet, you'll notice under chapter 8, there's a formula for DF. DF is degrees of freedom. To find your degrees of freedom, you just take n minus 1. Our n is just our sample size, right? So 45 minus 1 gives you a degrees of freedom of 44. So that's what's going to be along the left side of your t-score table. Then up along the top, you'll see it called area in the upper tail. Well, that's a fancy way of saying what's your alpha divided by 2, right? So your alpha in this case is 0.02, because if we take 1 minus 0.98, we get 0.02. So the area in the upper tail is 0.010, right? Or 0.1. Now, this is where you have to be careful, right? Because I think in that table you probably have area in the upper tail of 0.1, maybe even 0.001, right? So you need to make sure that you are looking at the area in the upper tail of 0.010. So our degrees of freedom are 44, and our area in the upper tail is 0.01. So if we follow and see where those two intersect in the table, we get a t-score of 2.414. So that's how we find a t-score here. In the next part, our confidence level is 90%, and we have a sample size of 38. Well, we're going to follow the same process again here. We first find our degrees of freedom, right? Our degrees of freedom are n minus 1. Our n in this case is 38. So 38 minus 1 gives you a degrees of freedom of 37. Now, we need the area in the upper tail. That's alpha divided by 2, right? So our alpha is 0.10. We get that by taking 1 minus 0.9. And we take that 0.10 and we divide it by 2. And we get an area in the upper tail of 0.05. And now we follow the same step again. We find our degrees of freedom of 37 and our area in the upper tail of 0.05. And we find that our t-score is going to be 1.687. Now the last part, 70% confidence and a sample size of 15. So, we've been finding our degrees of freedom first, right? N minus 1. Our n in this case is 15. So if we do 15 minus 1, we will have a degrees of freedom of 14. Now we need to find the area in the upper tail. Alpha divided by 2. Right? Our alpha is 0.3. We get that by taking 1 minus 0.70. So 0.3 divided by 2 gets you an area in the upper tail of 0.150. So if we look at our degrees of freedom of 14 and our area in the upper tail of 0.150, you get a t-score of 1.076.